This is Chapter 12, Surveying the Stars for Astronomy 100. In Chapter 12, we're going to look at the different properties of stars, the patterns among stars, and finally star clusters. First, the properties of stars. Our goals are: how do we measure stellar luminosity? How do we measure stellar temperature? And how do we measure the stellar masses? How do we measure stellar luminosity? Well, we have light coming from a star, and as it spreads out into space, the amount of light that we see decreases. So the brightness of a star depends on both the distance and the luminosity of the star. Obviously, the farther away we are from the star, the less bright it will appear. So luminosity is the amount of power a star radiates, and we measure that in watts. The apparent brightness is the amount of starlight that actually reaches us, that we see in our eyes or through a telescope. So luminosity is the actual amount of light being given off. The apparent brightness is what we see on Earth as an observer. The luminosity passing through each sphere, as we see here, is the same, but if it's over a larger area, then it's going to naturally appear dimmer. So the relationship between apparent brightness and luminosity depends on distance. We can determine a star's luminosity even as we can measure its distance and apparent brightness. So we can find luminosity if we can measure distance, and we can measure apparent brightness. Distance is the one that can be tough, obviously. So how far away are different stars? Well, in order to find out a distance, we need to have some sort of measuring device. In this case, we can use a topic we've covered before. It's called parallax, where the shifting of the star against some background stars is actually measurable in degrees or fractions of a degree, and that can give us the distance to the star. So there's actually two different scales we use for brightness. The first is called apparent magnitude, and that's noted with a lowercase m. So what we see from Earth is called the apparent magnitude. The absolute magnitude is what we would see of the star if it was placed a certain distance from Earth. So in order to fairly judge the brightness of stars, we use absolute magnitude, because then distance is not a variable. The only variable is the actual brightness or luminosity of the star. So how do we measure stellar temperature? Well, this chart is pretty important because it gives us the spectral sequence of stars, the actual classification system used to measure temperature. Going down the left-hand side, we have spectral types, and those spectral types are noted by the letter that you see: O, B, A, F, G, K, and M. The second column gives examples of these star types. The third column gives the temperature range that these star types would have. Something like our Sun is a G-type star, having a surface temperature of between 5,200 and 6,000 kelvins. There's absorption lines, there's brightest wavelength, and of course over on the far right are sample spectra for those particular types. So any star we should be able to classify any star into one of these spectral types. And of course every object emits thermal radiation with a spectrum that depends on its temperature. So an object of fixed size grows more luminous as its temperature rises. So in other words, if we don't change the size of the star, but we increase its temperature, we measure that temperature, and that determines its luminosity. As we've learned before, hotter objects emit more light per unit area at all frequencies, and hotter objects emit photons with a higher average energy. So obviously the hotter an object is, the more to the left or shorter wavelengths will be visible in its spectrum. So here's the range of temperatures for stars. The hottest stars could be as high as 50,000 Kelvin. The coolest stars as low as 3,000 Kelvin. And of course the sun's surface, the sun's photosphere, is around 5,800 Kelvin. So it's on the cooler side. The level of ionization also reveals a star's temperature. So in other words, the hotter a star is as you go up in this diagram, you get different types of ionization of the atoms or molecules. So that's something that's detectable as well. So a line or different lines in a star spectrum correspond to spectral type. And again, those types are classified as going from hottest to coolest, O, B, A, F, G, K, and M. So you can use any mnemonic you like. Here's two that might be memorable, but in some way you do need to remember this order, because if a question is asked which is hotter, a B-type star or an F-type star, you would naturally say a B-type star. Here are some of the people who were pretty instrumental in figuring out this stellar classification system. These were, for whatever reason, called calculators, people who were able to somehow, through the spectrum of a star, classify the star into a spectral type. So how do we measure stellar mass? Well, we need a binary star system to do that, because mass is directly related to the brightness of the star, or the apparent brightness of the star. And as you can see, going from left to right, the brightness of the binary star system varies depending on the position of one of the stars orbiting the other. So the orbit of a binary star system depends on the strength of the gravity of the binary star system. And if we know that, we can actually calculate the mass of a star. There are three types of binary stars: visual binary, eclipsing binary, and spectroscopic binary. And as it turns out, there are quite a few star systems out there that are binary star systems, including ones we can see from Earth. Here's an example of a visual binary star by actually observing one star moving around the other. And again, eclipsing binary stars can be viewed in terms of varying brightness as one star orbits the other. A spectroscopic binary star is, again, a pair of stars, one orbiting the other, where we see a shift in the we see a Doppler shift in the wavelengths of light. So as the star might be approaching us, we'll see a blue shift. Moving away from us, we see a red shift. So we can measure the mass by using gravity. That gravity is determined any one of those three ways. We don't have to worry about the mathematical formula, just understanding that the period of revolution and the separation between the two stars can be calculated, and by that we can actually measure the mass. So as we've found in surveys of stars, we see that the most massive stars are as much as 100 solar masses, and least massive stars are as low as 0.08 solar masses. And of course the sun's mass is 1.0. 100 solar mass stars are pretty rare. 0.08 mass stars are also fairly rare. So again, our sun is 1 solar mass. So how do we measure stellar luminosity? Well, if we can measure the star's apparent brightness and distance, we can compute its luminosity with the inverse square law, something we're not going to actually calculate, but we'll use as we go through the rest of this chapter. Parallax will tell us the distance to those nearest stars, though. And how do we measure stellar temperature? Well, a star's color and spectral type both reflect its temperature. So if we find its color or its spectral type, we can get its temperature. How do we measure stellar masses? Well, Newton's version of Kepler's third law tells us the total mass of a binary system. We can measure the orbital period, the orbital separation. We can eventually calculate the mass of a star. In this section, we're going to look at something called the Hertzsprung-Russell diagram, or HR diagram. What's the significance of the main sequence, and what are giants, supergiants, and white dwarfs? Here's what we call the Hertzsprung-Russell diagram. It's a pretty important part of this chapter since it shows you where most of the stars will reside during its lifetime in terms of temperature and luminosity. This is the way stars are classified. So we're looking at a diagram similar to what you see on page 318. Luminosity and temperature are the two big factors that classify stars. In an HR diagram, temperature is on the bottom, but temperature goes to cooler temperatures as you go to the right, not to hotter. So it starts out with hot temperatures on the left, cool temperatures on the right. Luminosity is on the left side, and as you go up on the scale, luminosity increases. So as it turns out, if we were to plot several thousand stars, we would see that most of the stars reside on what's called the main sequence. That's the band of stars going from upper left to lower right on the HR diagram. Stars with a lower temperature and higher luminosity than main sequence stars must have a larger radius. So we call those giants and supergiants, and they're normally off to the upper right. Then we have stars with much higher temperatures but lower luminosity because they're smaller. Those are called white dwarfs. So they would be in the lower left of the HR diagram. And then we have one other factor. The star's full classification includes the spectral type and luminosity class. So we have these Roman numerals that designate the star, basically the star size or position on the HR diagram. Supergiants, bright giants, giants, subgiants, and those on the main sequence. So an example such as the Sun, we know it's a G-type star. Well, it's a G2 type star. We subdivide each letter into 10 parts. And because it's on the main sequence, it's a type 5. So our Sun is a G2-5 star, as opposed to maybe a star like Betelgeuse, which is a red supergiant. It's a very cool star. It's an M2 type star, but it's a supergiant. So it's an M2-1 star. So the HR diagram gives us a lot of information about stars. It can tell us the temperature, the color, the spectral type, of course the luminosity of the star, and even the radius of the star, depending on where it is. So what's the significance of the main sequence? Well, main sequence stars are fusing hydrogen into helium in their cores, like our Sun. So they're basically stars which are stable. They're not burning other elements other than hydrogen, and their lifetime is for the most part on the main sequence. Luminous main sequence stars are very hot, so they'd be in the upper left. And less luminous ones are cooler, yellow, or even red, and they're in the lower right. But they're all on the main sequence. So basically, main sequence stars are stars that are burning steadily, they are stable, and they spend most of their lifetime on that main sequence. As you can see from the upper left to the lower right, though, their lifetime varies. In this case, anywhere between 10 to the 7th years, which would be about 10 million years, and down toward the bottom, 10 to the 11th years. High mass stars are normally found in the upper left, and low mass stars are usually found in the lower right on the main sequence. The mass of a normal hydrogen-fusing star determines its luminosity and spectral type. So it's mass that really dictates where a star will be on the main sequence. Obviously, the higher the mass, the upper left is where it's going to be, the lower mass toward the lower right. So here's some variations in the qualities of a star. Luminosities can vary anywhere between a 10,000th the luminosity of the sun to 1,000,000 times the luminosity of the sun. Temperature we've already talked about, and of course spectral type is determined by the temperature of the star. And then mass. We have a variation in the mass of a star. So all of these qualities can be put together and a star can be plotted onto the HR diagram. Our sun, based on the mass of it, has an expectancy of about 10 billion years. So most of the astronomers think our solar system's about 5 billion years old. The expectancy of our sun being 10 billion years, our sun has gone through about half of its lifetime. The core hydrogen, 10% of its total is used up so far. So we can, although it's not an even fraction, we think our star will last about 10 billion years. Our calculations show that stars that have more mass than our sun, will last a shorter period of time because they will burn faster. So for example, a 10 solar mass star might only last about 10 million years, whereas a star with 1/10 the mass of our sun could last as long as 100 billion years. So here's a summary of the main sequence stars and some examples, which is kind of interesting. A star like Spica, which is a B15 star, is 11 solar masses in size. We expect its lifetime to be about 10 million years. Whereas Proxima Centauri is on the other side of the scale here with a low luminosity. It'll live a long time. It has a very small radius and it's red in color. So let's look at exceptions beyond the main sequence: giants, supergiants, and white dwarfs. Stellar properties depend on mass and age. Those that have finished fusing hydrogen to helium in their cores are no longer on the main sequence. Stars can become larger and redder after they've exhausted their hydrogen, and in that case we can call them giants or supergiants. And most stars end up being very small and white after fusion has ceased. We call those stars white dwarfs. So giants and supergiants are far larger than main sequence stars and white dwarfs, and as you can see, Betelgeuse is a good example of a supergiant. Compared to Earth or a white dwarf, they are much, much smaller. So we're going from left to right here. We're kind of decreasing the size by 10 times. So which star is most like our sun? Well, as you can see, there are different regions of the HR diagram we've already talked about. A would be an area for white dwarfs, B and D would be on the main sequence, and C would be a region for supergiants. So, what's a Hertzsprung-Russell diagram? Well, it plots the luminosity of stars versus surface temperature. And what's the significance? Well, normal stars that fuse hydrogen to helium in their cores are normally on the main sequence, and a star's mass determines its position along the main sequence. A high-mass star will be luminous and hot. A low-mass star will be faint and red. And then what are giants, supergiants, and white dwarfs? Well, all stars become larger and redder after the core hydrogen's exhausted. They become giants and supergiants, and most stars end up as tiny white dwarfs after fusion has ceased. So they're hotter, but they're much, much smaller. Last but not least, let's look at the section dealing with star clusters. What are the two types of star clusters, and how do we measure the age of a star cluster? Here's an example of some open clusters, and as the book described, these are normally found within the disk of our galaxy. They might be a few thousand loosely packed stars. A globular cluster could be up to 1,000,000 or more stars in a dense ball, and since we have these stars very close together, they're bound by gravity. These stars, or globular clusters, are normally found within the halo of the galaxy. In other words, in sort of a spherical arrangement around the center of our galaxy. So how do we measure the age of a star cluster? Well, the Pleiades now has no stars with a life expectancy less than 100 million years. And there's something here called the main sequence turnoff. That's where these stars are leaving the main sequence depending on their age or depending on their mass. The main sequence turnoff point, as it's called, is an indicator of the age of the cluster. So if we can see stars that are not on the main sequence but forming a pattern, in this case of a bunch of yellows here, lifetime being about 10 to the 10th years, we're assuming that that's the age of the cluster. A detailed modeling of the oldest globular clusters reveals that they are about 13 billion years old. So in other words, if we take a group of stars that have this cluster characteristic and they are falling off the HR diagram, we assume that that's the age of the cluster. So what are the two types of star clusters? Well, there are open clusters containing a few thousand stars loosely packed in the disk of the galaxy. And then there are globular clusters that are more densely packed, containing more stars, and they are found within the halo of the galaxy. So how do we measure the age of a star cluster? Well, a star cluster's age roughly equals the life expectancy of its most massive stars still on the main sequence.